Johnny here with Simpson Math, and in this video we're going to continue graphing the trig functions, but we're going to learn the order in which to do the transformations when we are given multiple transformations. So if I have, we've covered 6 so far. Actually, let's just walk through it. So here I have written y equals a, some leading coefficient, being multiplied by the function, which represents any function, but we're specifically talking about trig functions. And inside the argument of the trig function, we have a coefficient and maybe a plus or minus sign, that translation. And then outside the function, we have another plus or minus d, so another translation. So if we're given all 6 of these, I only see 4 letters, but there's 6 there, how do we handle it? Let's just walk through those transformations one more time. A is simply multiply those y values by a. So it's a vertical dilation. If a is 5, we'll take the y values, multiply them by 5. That'll be a vertical stretch. If a is a third, we'll multiply the y values by a third, and that'll be a vertical compression. Those are vertical dilations. Now there's something else that goes with a, and that's if a is negative, then that is a reflection about the x-axis. Again, it's affecting the y values. So you can think of any positive y value like 3. When I reflect it down below, the y value becomes negative 3. So A is taken care of. B, well, remember that's going to affect your period of a periodic function. This is a horizontal dilation. And this one's a little bit counterintuitive maybe. If b is a number like 5, we're actually going to multiply the x values by 1/5, which is going to, do that. If x is a fraction less than 1, so something like a third, we'll multiply those x values by 3. So that's the horizontal dilation, compression and stretching. And like A, if B is negative, it's a reflection, this time about the y-axis. Again, it's affecting the x values. So if you have a positive x value, it's reflected to the negative axis. C is the horizontal translation. And it kind of goes maybe the opposite direction that you want it to go. This minus C will actually go in the positive direction C, or right C. If you had a plus C, it would go in the negative direction C. And then out here at the very end, we have a D, which is a vertical translation. So we've covered these 6 transformations in previous videos, and I claim so far I've given you ones that an order would not necessarily matter. If you had a function with more than one transformation, I've given you nice ones. But let's talk about the order. If I want to graph a function like that one where I have all 6, there is an order in which we need to follow. And the first thing we take care of is that b. So what I'd like to do is sketch one period of our function. So notice I'm just dealing with the b right now. And then I may have mentioned this before, I have it written above me as well. We can always find the period of a function by taking the parent's period and multiplying by 1 over b. Just like we would to find those new x values, we can find the new period by multiplying by 1 over b. Or you can think of it as dividing by b. the parent period divided by b, or the parent period multiplied by 1 over b. So if b was 2 and you were dealing with a cosine, well, the cosine normally has a period of 2 pi, but if b is 2, you're dividing by that 2. That's going to reduce its period down to 1 pi. So figure out that new period, take care of that, and draw your function over the new period. Take care of b first. Take care of that horizontal dilation. Now, if b is negative, we'll take care of that as well. So b still, if b is a negative, go ahead and reflect that function about the y-axis. Now this is, if you do have a reflection about the y-axis, you may want to pick your interval wisely. Let's say you have a cosine wave that starts at 0, because you decide to do that, and you draw it out to 2 pi to show a full period, but then you have to reflect it to the other side of the y-axis. So on your paper, you've drawn all the way to 2 pi, and then you need to go all the way to negative 2 pi. Well, 4 pi is hard to, like an interval of 4 pi is hard to fit on a sheet of graph paper, unless you scale it down. So smartly maybe is, if you have a reflection about the y-axis, to put the y-axis smack dab in the middle of your graph. You would draw cosine then from negative pi to positive pi, and that way when you do the reflection, well, you're still in that same window. You're still in that same interval. So I claim if you're going to have to reflect about the y-axis, or if you've got a negative b, just put that y-axis smack dab in the middle. All right. After b, we're going to take care of still working on the inside of the parentheses. So the b was inside. Take care of that first. I claim let's stick within the parentheses, and let's take care of c next. So we take care of the horizontal translation. After c, we kind of want to follow that same pattern where we take care of the multiplication before we do the addition. So let's take care of a first. If we have an a, well, we simply multiply those y values by a. I have written here, we're just vertically dilate by a factor of a. Oh, I'm using absolute value bars here just to mean I'm not worrying yet about the negative sign. So for b, I just want to know that b value. And then in my step 2, this is where I worry about it being negative. Same here. I'm going to multiply those values by a, and then if a is negative, I can maybe reflect that as a different step. As you progress and do more and more of these, you can maybe combine steps like this together, but I say for your, working through this first time, do one step at a time maybe. And then lastly, we'll take care of that d. Any vertical translation, that's the easiest part, but we're going to do it last. So if we go in order, we have b, c, a, d. Step 1 and step 2, this dealt with worrying about the b. Then we had c, and then these two are worrying about a. And lastly, we take care of d. B, C, A, D. Go in that order. A way to help you maybe remember that order, B, C, A, D, is the way we do our calendar year, like our years. Like Pythagoras was around 500 BC, that before Christ that we use. And then Newton was around 1700 AD. So it's BC and then came AD. That's just maybe a helpful way to remember the order. BCAD. BCAD. Take care of the period change, reflect over Y, take care of the translations horizontally, take care of your A's, then take care of your D's. All right. Let me do some examples and grab some graph paper. For my first example, I have y equaling sine of 1/2 x plus pi thirds. Ooh, there is something new here as well. So I've got to worry about, here's it. I like to ask this in class. What is my b in this scenario? And then what is my c in this function? What's my b? What's my c? I think we are all okay with saying that b is 1/2. But if you said pi thirds for c, you're wrong. So there's something wrong with the setup of this function. And if you just take a look above me, let's see, right there, notice there's something weird about that b. That b has its own set of parentheses. That b coefficient on the linear term, or this coefficient on the x term, it needs to be factored from every term in the parentheses. I need to multiply that 1/2 by the x and multiply the 1/2 by something to get pi thirds. All right, so I need to factor this thing. This is something new for my lecture videos, but it's not too bad. I'm going to pull out the 1/2. That is, I'm going to factor both of those terms by 1/2. I'm pulling it out, and then, it's just division or reverse multiplication. 1/2 times what would give me 1/2 x? Well, x does that. 1/2 times what would give me pi thirds? Well, let's think about that. 1/2 times what would give me pi thirds? Or you could think of it as division. If I had this equation, I could divide by 1/2, which is multiplying it by 2. But I think if I were to say 2 pi thirds, that's my guess. So 1/2 times 2 pi thirds, the 2's would reduce, and that would leave me with pi over 3. So if I factor 1/2 from pi thirds, I will get 2 pi thirds. You can always check if you guessed like I did, if you just kind of like, what would it be? You can always multiply just to verify. 1/2 times 2 pi thirds, the 2's reduce, leaving me with pi thirds. If this guessing didn't quite do it for you, you can go back to the equation and you can set up an equation. 1/2 times something has got to be pi thirds. So if I want to solve this equation, I can go through it. I can divide both sides by 1/2. Well, 1/2 times or divided by itself is just going to be 1. And then pi thirds divided by 1/2. A lot of my students know like that keep, change, flip. I guess I'll do that for fun. Pi thirds, you change the division problem to multiplication, and you multiply by the reciprocal of what's below. 2 pi thirds. So that's, if you need to do some sort of like off to the side arithmetic, have at it. Okay, so before I graph this, I'd like to identify my transformations. I claim that I've got an A value. Actually, let's go in order. B, C, A, D. I do have a B. Yeah, that's not an A, that's a B. I've got a B value of 1/2. That is simply going to multiply my x values by the reciprocal 2. It's also going to change my period. Sine normally has a period of 2 pi, so my parent's period, or the period of my parent, 2 pi. times 1 over b, or simply 2, is going to be the period of my new graph. That's going to be 4 pi. Oh, wow. Okay, yeah, 4 pi is going to be hard to fit on this if I use an increments of pi twelfths. So I may have to change my scale some. But I've got a new period of 4 pi. I can take care of the b by multiplying my x values by 2. Cool. Then I've got a c value of negative 2 pi thirds. If the minus sign confuses you, that's okay. It's basically a distance of 2 pi thirds, and because it follows a plus sign in the given function, I'll be moving in the negative direction or left. Two pi thirds. All right. I think I'm good. I think I'm going to graph a sine wave that has a period of 4 pi, get those pretty points on there, and then see if I can translate them left 2 pi thirds. Let's see how I want to do this. I think I'll just go from 0 to 4 pi. But I will need room moving leftward to the left of the y-axis. Now, if I let every square be 1 pi 12th, this is like 2 pi right here. You need 24 squares to get to 2 pi. So I'm not going to have enough room on this one sheet of graph paper. So I'm going to let every square be 1 pi 6, or 2 pi 12ths. So normally, and I'm going to do the same skip dash dash dash. So I'm letting every half a square be pi 12ths. So I'm skipping dash 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 skip dash. And I'm letting that be pi halves. Let's see if that makes sense. 1 pi 12th, 2, 3, 4, 5, 6 pi 12ths. Yep. Skip dash 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 skip dash. There's 1 pi. Skip dash 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 skip dash. There would be 3 pi halves. Skip dash 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 skip dash. 2 pi. This is going to be good. Skip dash 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 skip dash. 1, 2, 3, 4, 5 pi halves. I've made one full revolution around the unit circle, and now I'm just continuing. Skip dash 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 skip dash. That's going to be 3 pi. Skip dash 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 skip dash. 5, 6, 7 pi halves. Skip dash 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 skip dash. There is 4 pi. There was no a value, so there's no changing my y. I think I'll just go with my normal let 4 squares be 1. So I will not go beyond those 2 values. And I think what I'll do is, in pencil, just very lightly graph a sine that has been stretched out to 4 pi. I know that stretching 0 is still going to be 0. Normally, pi 6 goes to a half. Well, pi 6 times 2 is 2 pi 6, or pi thirds. So I have stretched it out to here. I'm going to do that one more time. Normally, pi 6 maps to 1/2. but I'm having to go through and double all of these x values. So pi 6 doubled becomes 2 pi 6 or 1 pi third. All right. Normally pi halves maps to 1. You double pi halves, you're all the way to pi. Now that I have those 3 points, I don't really need to do any more multiplication. I can just use the fact that this sine wave is so symmetrical. I know the next value will be that third. Let's see. Should probably label my axes. If that's pi halves, pi thirds, 2 pi thirds, 3, 4 pi thirds, 5 pi thirds, 6, 7 pi thirds, 8 pi thirds, that's 9, and then 10 pi thirds. The next one will be 11 pi thirds. All right, so I can tell at 2 pi, I'll have another x-intercept on this sine wave, or sine of 2x. And that means at 5 pi thirds, I'll have another 1/2 value. Symmetrical. 7 pi thirds, I'll be touching negative half. 3 pi is where I will be negative 1. 11 pi thirds, I'll be back to negative 1/2. And 4 pi, I'll be back to 0. So that I have this really fast sine of 2x. I could graph this in red because red is dealing with just that thing. I just don't want to get my graph too busy. But what I just graphed was sine of 2x. All right. Now I need to translate left to pi thirds. So what I'm going to do is figure out how many squares 2 pi thirds is on my graph. Because of how I scaled this, 2 pi thirds is sitting right there. That's 1, 2, 3, 4. That's 4 squares. If you did not label your graph the same as mine, that may not be, there's going to have different, it'll be different. But on mine, 2 pi thirds is 4 squares. So I'm simply going to take these points and move them left 4 squares. Not 4 tally marks, but 4 squares. And some of these points are lining up real nice. Like that point that I just plotted was pi thirds, comma 1. It's already labeled. I don't have to worry about it. Some of these, though, like this one, and then this one, I am going to have to label because I do want those, at least the pretty points, to be clearly labeled. So I can read this one, 10 pi thirds, comma 0. 3 pi, comma negative half. 7 pi thirds, comma negative 1. 5 pi thirds, comma negative 1/2. 4 pi thirds is the x-intercept. Pi half. Pi thirds, 1. This is just going to be, well, that one's negative 2 pi thirds because that's how far I went. This one, every 2 is, 1 pi third, duh. And this is negative pi thirds. In orange, I'm going to graph my final sinusoid or graph. I'll label it sine of, I'll go ahead and use the factored version, but either one they're the same thing. 1/2 of x plus 2 pi thirds. So really the only new thing with this example was the fact that there was a b that I had to factor out. The b in the transformation rules affects the x and that c. So what we were given, the b was only being applied to that x. We're only multiplying there. So we need to factor it out, and in this form, then, we can apply the transformation rules. Change the period, shift. order may not have mattered there. If I took my sine wave, shifted and then stretched it, probably would have been okay. But in my brain, it's easier to stretch things out when you're dealing with zeros. Yeah, that just makes more sense to me. But the order does matter, and I'll show you in my next example, I think. Oh, I guess while I have a graph, I should talk about things like the period. We already mentioned, because that was basically step one, figure out the period before you graph it. And the period is going to be 4 pi. We stretched it out 4 pi, and then we shifted it. The shifted had nothing to do with the period. It has a period of 4 pi. The amplitude, well, there was no a, there was no coefficient outside the trig function, so it should just be the normal amplitude of 1. The domain is all real numbers. Of course, the sine wave goes on forever. Range, because there was no a value, that range is not going to be affected either. It goes from -1 up to +1, both included. X-intercepts, this might be a little bit challenging. Let's see. My strategy is to list a good one. 4 pi thirds. And then to that, add the distance to the next one. Well, from 4 pi thirds to 10 pi thirds, that's 6 pi thirds. Or 2 pi? Yeah, that's right. Plus 2 pi. Okay. Comma 0, because those are x-intercepts. So listed a good one, and then added the distance to the next. Put a k in there to represent every interval there on out. The y-intercept, now this may be a little bit too challenging. For my course right now, if it's not pretty, we don't worry about it just quite yet. I'm not worrying about, I don't want these graphs to be too algebraic. I just want them to be quick little, let's get them graphed. So if the y-intercept is easy to spot, list it. If it's going to require you to set the thing equal to 0 and start to solve for it, then I'm not too concerned with that right now. All right, do I know the value that is, looks like 2 squares away? Blah, blah, blah. Well, I should. Let's see, if pi 6 maps to 1/2 normally, pi thirds maps to √3/2 normally. Oh yeah. So yes, I know the y-intercept is at 0, √3/2. I can walk through that again. Let me write it down now before I forget. All right. So I just kind of thought about it for a second. I know on the normal graph, which I haven't graphed here yet, but on the normal sine wave, sine maps pi thirds to √3/2. Well, we just doubled everything. So now sine of 2x is going to be mapping 2 pi thirds, I'm sorry, 1/2 x, 1/2 x, 1/2 x, 1/2 x, to that √3/2. So at 2 pi thirds, on the gray graph, or the red graph, we have a point at 2 pi thirds, √3/2. And then we just move that over left 4, so 0, √3/2. We move that over a distance of 2 pi thirds, and there we are. All right, I claim y'all should be able to do that. So do it. All right, I think that's about everything. Again, the only new thing was factoring that b. Let's move to another example. All right, next example, I have a tangent wave where we have a -x plus pi halves. What's my a? Well, it's 1, therefore I don't care about it. What's my d? It is a +0, I don't care about it. What I have is some sort of b and some sort of c. What's my b value? I agree. My b value is -1. What's my c value? I say that was a trick question. That negative is only being applied to the x, not that c value. So just like I had a 1/2 before that I had to factor out, I have a -1 b value that I need to factor from both of these two terms. So my c is going to be a negative pi halves. So let me finish with b though. B is -1. Because of the 1 b value, I'm not concerned with it horizontally dilating. That's not going to change. My period is not going to change. When you multiply by 1, you still have 1. The negative, though, that means I'm going to have to reflect this thing about the y-axis. No change in period. I need to factor this thing. I probably should have done that before I written that down. But anyways, let's factor. Pulling out the minus sign, I'll be left with x minus pi halves. Always double check. The minus times the x is a negative x. The minus times a negative pi halves is the positive pi halves. It's clear to see that my c value is pi halves. Because it is now following a minus sign, like it's supposed to, we are going to be moving in the positive or the right direction pi halves. So you could imagine a lot of students seeing the plus pi halves and thinking, oh, I need to go left. But no. We need to factor out any sort of b value, so the b is being distributed to both. In this form, we can apply the transformation rules. So I have a b that's negative, reflect about y. A c that follows a minus sign, so I need to move right pi halves. Now before I draw my axes, I should maybe think about what is going to happen to my graph. It's going to reflect about the y-axis. Okay, that means I think I want to put my y-axis dead smack in the middle so that my graph, when I have it graphed, to reflect it about the y, I can just do this. It's just going to have that same interval just being reflected. If I had put my y-axis here, drew out the tangent wave, and then tried to reflect, well, I wouldn't have room on my paper. So I claim, let's do the interval from some negative region to some positive region. But I am going to have to move right pi halves. So, leave a little bit more room on the right. Okay. Now I'm graphing a tangent wave. So the tangent period is only a pi. That's nice. So I think I'll have plenty of room, even with shifting over pi halves, to use my normal, let every square be 1 pi 12. The hardest part is really just getting these axes labeled correctly. But I have on my graph a interval here of pi. So if I just graph tangent over this, then I've graphed a period or a cycle of tangent. Let me just in pencil graph tangent real quick. It has asymptotes at these pi, negative pi halves, it goes through 0. Pi fourths is a lovely 1. So something like that. So to take care of my first transformation b, BCAD, I'm going to reflect it off the y-axis. Nice and simple. The point that is at pi fourths, comma 1 will be reflected to negative pi fourths, comma 1. The point at negative pi fourths, comma negative 1 will be at pi fourths, comma negative 1. The asymptote at pi halves is reflected to the asymptote at negative pi halves. This vertical asymptote at negative pi halves is reflected to this vertical asymptote at pi halves. I'll do a little dashed line in here for this reflected tangent in red. What I just graphed was a tangent of negative x. Now I can take care of my next transformation, c. I can move everything right pi halves. This is nice and simple. Let's see, skip, dash, 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 skip, dash. I'm now going to go all the way to pi. That asymptote at pi halves is now an asymptote at pi. Label my axis so I don't get lost. The point at pi fourths, comma negative 1 will be shifted over to 3 pi fourths, comma negative 1. Nice and easy. I now have an x-intercept at pi halves. That point on the original tangent was reflected and then shifted, so now it's back on this new tangent. And then the x-axis itself has become a asymptote. It's kind of hard to graph asymptotes on the axis, so maybe like this color for sure helps, but I'm doing a little slanted dashed line for the asymptote. Do my best to put a little curve in this. I could go off and get those other values if I needed to, like the root 3s and the root 3 over 3s to help me flesh it out. But I'm done. I have graphed a tangent of negative x minus pi halves in orange. Now that should look familiar, but let's just continue with saying what we would normally say. The domain here, I got a problem at 0 and pi, so I'm going to say most x's work. The set of all x's such that, and then I'm going to list a bad one, and then add the distance to the next bad one. So because 0 is bad, we can actually do this. We can say every pi k is a problem. Actually, I'm going to say x cannot be those. X cannot be pi k. Range, I've got no problem. All the way up, all the way down. Actually, least to greatest, all real numbers. Period, it didn't change. I didn't have a value other than 1 as my b value, so the period is still going to be 1 pi for this tangent wave. Amplitude is really a dumb question. I would say this is the 0 position, so then how high does it go? But it doesn't, it just keeps going. What else we talk about? Domain, range, period, amplitude. Oh, intercepts. I for sure have an x-intercept. I'm looking at one. So I'll go ahead and list it. I'm listing the good one. And then I'm going to add the distance to the next one. I don't see it, but I know it would be at 3 pi halves. So that is just a distance of 1 pi. So every pi k after pi halves, I will have a x-intercept because this pattern just repeats. And then a y-intercept, no, because my y-axis has become an asymptote, so I will get really, really close to it. I'll approach it, but I'm not going to touch Okay, something hopefully you've maybe noticed by now is we know this orange graph. We know this curve that can't touch 0 or pi. It looks like a tangent, but it's been reflected the other way. We know a graph, one of our trig functions that crosses through pi halves. This orange graph is just cotangent. Gasp. This thing right here is just cotangent of x. Now why is that? Why did these two functions, when we graph them out, become this cotangent? I think I'll go back to my original one, this negative x plus pi halves. Some of you may not like that leading negative, so you may have even rewritten it. If you tried this one on your own, you may have said, you know what, I don't like leading negatives. That's the same thing as tangent of the pi halves minus an x. Negative 2 plus 5 is the same thing as 5 minus 2. Negative 2 plus 5 is the same thing as 5 minus 2. So you can rearrange those like that, as long as you keep the signs the same. And then in this form, we should maybe recognize this, that 90 degrees minus theta. This is that co-function talk. Oh yeah, we have an identity. Tangent of pi halves minus x is the same thing as cotangent of x. So from the very get-go, using no transformation rules, you could have used a co-function identity to say, oh, this is clearly just cotangent, and then graphed your parent cotangent, and you'd be done. All right. But that was another example of you having to factor out a b to apply the transformations. I think I got another example in here. None of these examples so far seem to have been the order stressing it out, like stressing with the order. I just had b's and c's, and both cases I did take care of the b and then take care of the c. Okay. My next example, I've got y equals 1 minus cosecant of x. So can you identify the a, b, c, d? Can you identify the transformations? If we're supposed to go in order, what is my b in this game? Well, b is the coefficient on the x. Okay, I don't have one. It's 1, so there's no b to worry about. Then comes c. C is the minus or plus sign inside the argument of the cosecant. I don't have one of those either. I got like a plus 0. No big deal. B, C, A. I think I've got an A. A is the coefficient on the function itself. Now don't be confused by that 1 out there. In fact, it may be beneficial to rewrite this like really in that form. I've got a negative cosecant function, and then that 1 is the d. It's just being written out front instead of behind. But we just said you could take a negative 2 plus 5 and rewrite it. So I'm going to add the 1 at the end instead of talking about it at the beginning, because I'm used to my d's being outside, like way out here. Okay, so I've got a value. I think it's clear to see this coefficient, the number multiplied by cosecant. The 1 was not multiplied by the cosecant. It was 1 minus the cosecant. So my a is a negative 1. And then my d is a positive 1. Well, a just means I need to reflect about the x-axis because it's negative. D plus 1, that's the easy translation. I'll move everything up 1. Oh, this is going to be easy. I've graphed cosecant enough times. I know what it looks like. I'll just very quickly get this down here. I'm showing from negative to positive. It doesn't matter. I'm not reflecting about the y-axis. The x-axis is up and down, so it doesn't matter. But I've already drawn my axes, so I'm going to go from negative pi to positive pi because cosecant has a period of 2 pi. So I need to show an interval of at least 2 pi. Cosecant is the reciprocal of sine, which is pretty at the 6's. So I'll go ahead and at least label the pi 6's. I know that these values will be reciprocated. That half will go up to 2. So I need to go up forever, but at least 2. Okay, I've labeled a interval of 2 pi. And I know cosecant. If sine was 1/2, it would be 2. If sine is 1, the reciprocal of 1 is still 1. 5 pi 6 is also positive 2. Now, 0 and pi, and even negative pi, will become asymptotes. So let me draw some asymptotes on here. Do a little dashed line because I'm about to do the y-axis. It's hard to see on the y-axis, so I'm going to do a little dashed line so I can really see it. I'm doing it in blue because that's going to be my final graph. In black, I'm drawing a regular cosecant. I should probably do that in pencil, but oh well. These are the pretty points. The sine and cosecant are pretty at the 6's. And then I can draw a little dotted maybe cosecant. So in gray and black, I've drawn just cosecant of x, the reciprocal of sine. In green, I'm going to take a step to reflect this about the x-axis. So all the points above are now below. The asymptotes themselves, I mean, you could think of them as being reflected as well. They're going to remain vertical asymptotes. And any negative y values will be reflected above. And you may notice that that cosecant graph, if I had incorrectly reflected about the y-axis, I would actually get what I needed. That's because cosecant is an odd function. If you reflected about the x-axis, it's the same thing as reflecting about the y-axis. But it's very important. This is why I make you identify the transformation and then tell me what you're doing. I need to know you're not just coincidentally getting the right answer. I need to make sure you know those transformations. So tell them to me. A is a -1, therefore it reflects about the x-axis. All right. I'm almost done. I just have to shift every point up 1 now. 1 on the y-axis is 4 squares, so this should be easy. Oh, and normally cosecant does not touch the x-axis. At this point right here, when I shift it up, will. So I'd have at least one x-intercept. I've gone off my y, so I need to label up there. 1, 2, 3, 4, that should be 3. The asymptotes, I mean, sure, you can move it up, but it's still going to be there. And in blue, I have graphed this. Nice and easy. I did go in order. I reflected before I moved up. I don't think it matters here. If I had taken that graph and moved up and then reflected, I would have gotten the same thing. So the order maybe didn't matter here, but go in order B, C, A, D. There are some in the homework that the order does for sure matter. You'll get the wrong answer if you don't go in that order. So B, C, A, D. Take care of the period. Change. Take care of any reflection about the y-axis. Then you can horizontally translate. Then you can take care of the amplitude, or multiply those y values, or reflect about the x-axis. And last, save the easy one for last, or vertical translations. Before I finish, I should talk about the domain. Well, 0 is a problem, and then every pi interval after that. So I will say all x's work, but I do have a problem at pi k. Range. This has been affected because I shifted up. My range is now different. I'm good from least to greatest. Negative infinity up to and including 0. Bracket around the 0. Union that with another interval. I kind of like pick up my pen and I start back up at 2, included, and then I go to infinity. So there's nothing between 0 and 2. All right. Period. We took care of that first. That was our first step. There was no change in period. So the period for cosecant is 2 pi. Amplitude. That's a dumb question. It doesn't really matter. From a 0 position, now we can talk about it. The 0 position is usually on the x-axis, but we shifted everything up 1. So my 0 position is now at 1. So then from 1, how high does this thing go? Well, it goes up forever, so there's no amplitude. So, but watch out for that. When you shift up or down, that 0 position is no longer the x-axis. So you have to kind of worry about, well, from the 0 position, how high does the wave go? It looks like my x-intercepts will be fun to talk about. Strategy. List a good one. Pi halves. Add to that the distance to the next x-intercept. Well, it's not 1 pi away, it would be 2 pi away. Basically, there's one x-intercept in one period. So every 2 pi seems to be good. Coordinate form, there is no y-intercept. All right, BCAD, BCAD. Tackle your transformations. Worry about period. Take care of that. BCAD, BCAD. I'll see you in the next video.